Everybody, Ethan here. Today I'm going to talk about neuromuscular junctions and myasthenia gravis. I want to start with something first by saying that I think the neuromuscular junction is really cool. I'm not saying that neurology as a whole isn't cool, right? I mean, you got neurons firing, that's pretty cool. But personally, at some point, I want the neurons firing to actually do something. And the neuromuscular junction, in my opinion, is one of the places where the doing something actually happens. It's like where the rubber meets the road, where the lighter hits the fuse, where the lame metaphor collides with the lame metaphor. And for lack of a better word or phrase, it's like where the action potential actually makes some action happen. Lame wordplay aside, I hope this uncovers a key truth or truths about me. I'm someone who really likes action. I'm all about action. But as long as we're only talking, though, about fictional action, because let's be honest, if we examine my attributes honestly, right? I'm someone who spends my day studying, reading books, and watching Netflix on the couch. I'm someone who's often startled by loud noises. And I'm someone who has the athleticism and real toughness, really, of an arthritic koala. All these attributes mean that if you actually put me in any action-adjacent, action-like situation, I'd be in probably a lot of trouble. But fictional action, books, TV shows, even the conceptual action of the neuromuscular junction, that's more my speed. Okay, that nonsense aside, let's move to what I actually want to talk about today, which is the neuromuscular junction, specifically answering these three questions. What is the structure of the neuromuscular junction? What does a neuromuscular junction do, and how does it do it? And what is myasthenia gravis, and what is its basic pathophysiology? I'm just going to say right out from the front, you can already kind of tell there's a lot of big words here, difficult to pronounce, especially when you're like me and don't pronounce words very well. I apologize in advance for when I stumble over my words in this video. Regardless, let's start with structure. In a nutshell, the structure of the neuromuscular junction involves lower motor neurons synapsing onto motor end plates. I want us to take a step back to look big picture, right? The neuromuscular junction sits at the end of this long pathway that starts in motor cortex here. This is the neuromuscular junction seen here. This is at the end of this very long pathway, right? You've got upper motor neurons, part of tracts, the corticospinal tract and the reticulospinal tract that travel down the brainstem, down the spinal cord, and synapse in the ventral or anterior horn of the spinal cord onto a lower motor neuron. That lower motor neuron then exits that ventral or anterior horn, which then synapses at the neuromuscular junction. I'm omitting a bit here. The first thing I've omitted are the cranial nerves. This pathway does not cover everything, right? And one of the things it doesn't cover is the cranial nerves. Stuff like, say, facial nerve action isn't going to travel way down the spinal cord if the eventual motor target is a muscle in the face. No, it's going to synapse in the cranial nerve nuclei in the brainstem, which will then give off a lower motor neuron to go to its target. Another thing that this pathway seen here doesn't cover is the autonomic neuromuscular junctions. And this is a quick aside, but this talk is really going to focus on the skeletal muscle innervation via somatic motor pathways. But I do want to acknowledge that autonomic neuromuscular junctions are a thing, and they're a bit complicated and different from their skeletal counterparts. For one, they have excitatory and inhibitory function, unlike the skeletal muscle neuromuscular junctions, which are really basically excitatory only with their nicotinic acetylcholine receptors. In addition, they sometimes don't even involve changing membrane potential at that postsynaptic cell. In short, it's different, they're complicated, and I'm not really going to go into this, and it's truthfully also because I don't fully understand it after the research I've done. I'm just going to sort of leave it at that and just know that these autonomic neuromuscular junctions are different than these skeletal neuromuscular junctions, and they do obviously exist. So let's go back to the skeletal muscle neuromuscular junctions, and let's focus and zoom in on where this lower motor neuron actually contacts the muscle. What you see in this figure here is a motor unit. What a motor unit is, it's a lower motor neuron and all of the connected motor fibers, or muscle fibers, I should say, not motor, muscle fibers that motor neuron innervates. You see here the fibers that are in this like dark red are arranged in these larger fascicles, and you also can see this one lower motor neuron actually does innervate a ton of muscle fibers. In truth, it's anywhere from like 100 to 1,000 individual muscle fibers. But I do want to zoom in further now. What actually happens at the contact point? At the contact point, you see in this beautiful Wikipedia image with my obviously beautiful handwriting and annotations, you see sort of what happens at that contact point, the actual junction itself. At the top of this image, you see the axon terminal of the lower motor neuron, and it's acting on the motor end plate, which is the specialized postsynaptic apparatus of a muscle fiber. You've got calcium channels. You've got vesicles filled with ACH. You've got ACH receptors. The question that this sort of begs, or this does beg the question, what does all this structure do? What is the function here? What actually happens? And that's the second part of this talk, right? In short, in a nutshell, it involves depolarization of the motor end plate to propagate an action potential on the muscle fiber. Let's talk now, and let me commit a cardinal sin of PowerPoints. I'm going to put a ton of text on the screen, but at least I will try to explain it. I want to talk sort of the order of operations and sort of what actually happens at this junction. You first start with the muscle cortex. It's like sending a command to move a muscle, right? You want to move my arm, like, let's go, right? That command travels down and eventually travels down to the lower motor neuron. That lower motor neuron is then, actually continues to travel down that, and it eventually depolarizes the axon terminal of that lower motor neuron, which causes the opening of these voltage-gated calcium channels I have drawn in here in blue, which allows calcium to rush in to this axon terminal. The rushing in of calcium, that influx of calcium, causes these vesicles, right? You see these red dots and these green circles. These vesicles are filled with ACH, and these vesicles will then, because of the calcium influx, travel towards the membrane of the terminal and fuse with the axon terminal membrane, allowing the ACH to be released in the synaptic cleft. So that releasing of ACH into the synaptic cleft allows ACH to then bind to the acetylcholine receptors at the motor end plate down here. Once those acetylcholine receptors are bound to acetylcholine, this opens these acetylcholine-gated ion channels that create depolarization, or an end plate potential that triggers an action potential that travels down the muscle fiber to cause contraction of that muscle fiber. And you can imagine the propagation of action potential down the surface of the skeletal muscle membrane, which will then allow for the entire muscle fibers, like all these sarcomeres and stuff, to contract. There is one additional concept I want to talk about in regards to this neuromuscular junction and its function. Oh my gosh, look at this rhyming. And that is the safety factor, or cushion of sorts, that exists at this junction. The change in membrane potential that happens when the ACH-gated ion channels are open, after, of course, ACH binds a receptor, is larger. That membrane potential change is larger than what's necessary to trigger an action potential to propagate down the muscle fiber. Right? I think opening the ACH-gated ion channels causes the membrane potential to change from negative 90 millivolts to negative 45 millivolts, which is really more than what's necessary to actually propagate an action potential to contract the muscle. This cushion, this safety factor, gives you wiggle room in terms of the amount of ACH needed to trigger an action potential, the amount of receptors that need to be there to bind. And we'll see this be relevant when we talk about dysfunction at this junction. And speaking of dysfunction, I do want to call back to one of the old videos I made on this channel, which talked about a potential area for dysfunction at the neuromuscular junction. I keep calling back to my old videos as if they're these great store of old wisdom, and they're not, right? Listen, it probably doesn't even deserve a citation, but I swear it's relevant here. Let me explain. We have acetylcholine being released in the synaptic cleft, right? And it's actually broken down by an enzyme called acetylcholinesterase, right? And that's important because if you don't break down acetylcholine in the synaptic cleft, you're going to continue the propagation and triggering of depolarization action potentials at that postsynaptic cell, because the acetylcholine will keep binding and stay bound to those receptors on the postsynaptic cell. So what happens, say, if you inhibit acetylcholinesterase via an acetylcholinesterase inhibitor, well, you can cause prolonged muscle contraction, which makes sense, right? Because the constant amount of acetylcholine in that synaptic cleft causes constant binding to the ACH receptor, which causes constant opening of the ACH-gated ion channel, causing constant depolarization at that postsynaptic motor end plate. Apologies. So this is one way that you can have dysfunction at the neuromuscular junction, but it's far from the only way. And a prime example, in fact, the most common example clinically, is a disease called myasthenia gravis, which will be the last part of this video. In a nutshell, myasthenia gravis involves an autoimmune attack on ACH receptors and other motor end plate membrane proteins, right? When we look at this diagram we already see here, we talked about how the acetylcholinesterase inhibitors could prevent ACH breakdown of the synapse, and that can cause overactivation, prolonged muscle contraction, right? But a key part in causing overactivation via an acetylcholinesterase inhibitor, or even activation at all, is the actual acetylcholine receptor itself, right? You can't depolarize this motor end plate without binding of acetylcholine to the receptor to then open the ion channel. And without a functioning receptor, you can throw on all the ACH you want. It's not going to have the same effect on the motor end plate. That's the basic pathophysiology of myasthenia gravis. So as I sort of hinted to or said outright, I should say earlier, myasthenia gravis is the most common neuromuscular junction disorder of skeletal muscles. It involves the creation of autoantibodies target against the nicotinic acetylcholine receptors down here in this photo, as well as the other membrane proteins that are on that motor end plate. So it's going to target those nicotinic acetylcholine receptors and many other membrane proteins at this motor end plate. These autoantibodies can do a lot of things. In one subtype of disease, they can actually activate complement and as such destroy ACH receptors. And even if they didn't do that, they also have other options. They can simply bind to these protein complexes on the membrane and thereby lead to dysfunction and the failure to open the ion channels that are necessary to propagate an action potential at the motor end plate and muscle as a result. And I sort of talked about before about the safety factor or the cushion between the actual potential change needed to trigger an action potential and the actual potential change that happens when these ACH ion channels open. That safety factor helps explain some of the symptoms of myasthenia gravis. I've seen in this Google picture seen here, a lot of the symptoms of myasthenia gravis involve muscles all over the body, right? You have muscles being affected in the eyelids, the mouth, the throat, the oculomotor muscles, as well as the limbs, right? And critically, the weakness tends to improve with rest and worsens with activity. This actually makes sense given the safety factor, the cushion between the actual potential change triggered when you open an ACH channel and the actual potential change needed to actually propagate an action potential. The safety factor explains this improving with rest and worsening with activity because as myasthenia gravis attacks those channels, the cushion that's built in the system starts to go away, right? Because you're losing the channels that can trigger an action potential. So as you continue to attempt to stimulate the muscle activity, you get closer and closer and closer to your threshold, lower now due to the myasthenia gravis, and eventually the cushion runs out and you can't generate an action potential to contract the muscle. So over time, right, as the muscle keeps getting activated, you're not going to get that same depolarization. And eventually, because the safety factor is lower, given this autoimmune attack, that can explain why you have worsening activity and improving with rest. I hope that sort of made sense. It's just sort of a way for me to hopefully illustrate some of those concepts we talked about earlier. But in short, what do you want to take away from myasthenia gravis? It's an autoimmune attack on those nicotinic acetylcholine receptors and other membrane proteins. So that in mind, let's review and take a bigger step back about what actually I talked about today. The first question I wanted to answer is, what is the structure of the neuromuscular junction? And in short, it's a lower motor neuron axon terminal synapsing onto the motor end plate. And then we got one lower motor neuron synapsing on many different muscle fibers. Second question is, what does a neuromuscular junction do and how does it do it? An action potential in an axon terminal leads to calcium influx, causing acetylcholine release. Acetylcholine binds to acetylcholine receptors on the motor end plate, causing the opening of ACH-gated ion channels, which cause depolarization and action potential propagation down the membrane of that muscle. Lastly, what is myasthenia gravis and what is its basic pathophysiology? It's the most common neuromuscular junction disease of skeletal muscles and involves autoantibody binding to ACH receptors and other membrane proteins at the motor end plate. So that's all I've got for you today. I hope this made at least some bit of sense and maybe was a little bit helpful or educational. These are the references I consulted for the video. I wish you all the best. Take care. Have a good one. Bye-bye.